Good afternoon, and considering the viewers we have today for this webinar, also good morning and good evening. My name is Frank Verbergen, and today I'm hosting this webinar on novel drilling technologies to accelerate the heat transition. Gladly, I'm not alone, so I have with me here today my colleague Andreas Reineke from TNO, Jan-Jette Planger from Canopus Drilling Solutions, and Liam Lyons from GA Drilling in Houston. So today, after a short scoping introduction for myself about the heat transition in Europe and the Netherlands, I would like to give the floor to Andreas Reineke, who will talk about who will give an overview of emerging drilling technologies. Hand over to Jan-Jette, who will talk about directional steel shot drilling. Before we shift to Houston, where Liam will talk about how to make the geothermal anywhere a reality. And we will close off this session with a panel discussion and questions. So just as an introduction, how does this interactive webinar work? We invite you actually to ask questions. You can do that by using the button below at the right bottom in the video screen. If we cannot answer your questions today, we will follow up and we will connect to you after the webinar to provide you with the answers where possible. This webinar itself can be watched online on demand at tno.nl. So I would like to start with scoping a little bit on why we're having this webinar today and talk about the heat transition in Europe and the Netherlands. So last week we have seen the closure of the COP29, and although there were I think some heavy debates about who's going to pay for what measures throughout the world, I think there's a general consensus that we need actually to take some actions regarding the climate. And also we need to shift from oil and gas towards more renewable resources for our energy. And with that, there was also a call for action to actually take some steps towards the production of energy. And what I would like to point forward also is this is an editorial paper from Nature that clearly states that we need the subsurface, and we also need the geologists and the engineers, etc., who work in the subsurface to bring us actually all the requirements that we need for this energy transition. So that can be in the part of mining for the critical raw materials, but also the topic that we're discussing today is about CCS. It's about hydrogen storage. It's about the storage of heat, etc., etc., and of course geothermal. Well, we're based in the Netherlands, and if we look into the situation that we have here in the Netherlands, some colleagues of mine they have actually done the modeling on what it actually takes to reach the agreed targets for the Paris Agreement. And if you take the subsurface out of the equation, there's just no way that we're getting towards the goals that we need. So we need the whole portfolio of options that the subsurface actually can offer, whether that's geothermal, hydrogen storage, carbon dioxide storage, heat storage, and geothermal. And if you then zoom in a little bit towards the geothermal situation that we have here in the Netherlands at the moment, we can actually see that there are several options and several technologies that we're deploying at the moment. So on one end, there's the open geothermal systems, which in the Netherlands are usually at the depth of around 2 kilometers, 2 to 3 kilometers. On the other hand, there's a major effort in development of the ATES systems, so the aquifer thermal energy storage systems that usually are developed at a depth of around 200 meters, but can be slightly deeper. And we have the closed systems, the BTES systems, that actually are developed for most part at now down to around 150 meters, but there are some developments that actually take this development also deeper. What these three things, although they are all part of the geothermal family, is they all require quite specific drilling technologies and drilling techniques. And with that, I would like to pinpoint out and point out that drilling as such is not new. We've been drilling as an industry, I think, for decades, even going probably millennia back when the first drilling operations were taking place in China. We have, I think, in the recent years, drilled further, drilled deeper, drilled complex reservoirs, etc., etc., etc. But what we're facing now is actually we have a little bit of scope change towards carbon dioxide, towards hydrogen, towards heat. And what these technologies also have in common is that the business cases are more marginal than we are used to in oil and gas. So it also means that in terms of competition towards oil and gas, we are, from an energy for the energy transition, we are probably on the we probably need to be more competitive in other ways. So that we will require new developments and new developments that are probably dedicated towards the purposes that are requested. So with that, I'm representing here the Rijswijk Center for Sustainable Geoenergy, and what we try to do is actually we try to accelerate the implementation of new technologies for the energy transition. We do that by experimental testing at a one-to-one scale, and from that research is also basically some of the topics that are being handled and discussed today. I think they're put on the spotlight here. And with that, I would like to hand over to my colleague Andreas, who can take the floor.
Yeah, thanks, Frank. Yeah, and I'm very happy today to talk about the overview of emerging drilling technologies. I'm Andreas Reinecke. I'm the lead scientist, well technology at TNO. And yeah, these emerging drilling technologies I'm talking about are really here for geothermal provision and for the subsurface as well, and is really going for the shallow, the deep, and the ultra deep resources. Yeah, and Frank mentioned it already. We have a family, let's say, of geothermal solutions nowadays, and we're really going from what you see here very much to the left is really to the ball heat exchangers, couple of 100 meters deep. Yeah. And to buffering solutions where the first 100 of meters are really used for storage of heat and then extraction of heat again. This is not classical geothermal, but we need a lot of drilling for this as well and good technologies for this as well. And then here in the middle we come to the low and mid temperature extraction. So that's what we classically know, the medium depths. Yeah. So greenhouses, heating of greenhouses is a very good example for it. And that goes then already to the about 3 kilometer depths really to have the heat provision up to 150 degrees C. And the next step, and there we see quite some exciting developments as well at the moment, is really going deep, going very deep, drilling into the basement, into the hard crystalline rocks that we have, and develop your reservoir, actually build or engineer your reservoir down there. On the one hand with the enhanced geothermal systems, where then fractures are created between the well bores and water circulated, or even the advanced geothermal systems, the deep closed loop solutions. And all this needs very different kinds of drilling technology developments. Yeah? And if you're looking at the trends and the potential at the moment in Europe, I mean, there are already quite some great improvements going on here. On the left side, you have a recent map of the heat and electricity production in Europe, coming from the EGEC market report 2023. And yeah, there's heat in Europe. We have now 6.3 gigawatt thermal already produced from geothermal. And if you look into the Netherlands, yeah, then even if you look at by area of the Netherlands, and the Netherlands is even doing best, yeah, in Europe. But interestingly, still the potential on top of it, yeah, is even much higher. So we have at the moment 0.2% electricity from special places, special locations in Europe, and 2.8% of heating and cooling. And if you look into the potential, which is laid out in the plans, yeah, for the EU, yeah, then we can even get a factor of 50 higher in electricity provision and a factor of 10 higher in heating and cooling. And yeah, what you have here in the center is you could, where is this heating and cooling? Where is this output? Where is this coming from? In the center, we have a global review of the direct utilization of geothermal, and what you see is the industrial really is not really taking off. There are some improvements, yeah, but it takes quite a while. But where really the terajoule per year are produced are the ground-sourced heat pumps. So the shallow to mid-depth systems, a lot of them are really shallow drilling, ball heat exchangers installed, yeah, and from there these terajoules here are produced. And I can tell you, if you look at these numbers here, obviously these are millions of meters that have been drilled and need to be drilled in future as well. Let's look at the challenges of shallow and medium depth resources. Yeah, and shallow, the drilling itself is not in shallow resources. The drilling itself is not difficult. This is fast. Yeah, so this is well known. Yeah, and relatively cheap, you could say. But what is the challenge here as well is the space limitations. Quite often you're in an urban environment there where you need your heat. Yeah, and you need to put your rig somewhere. And you have quite some noise limitations. You cannot operate during night usually, yeah, so you really need to take that into account. Yeah, you want to have electric-driven systems, yeah, for your emissions. Yeah, you have silent drilling systems as well. And then mid-depths, yeah, usually the space there is not the challenge anymore. But the challenge what you have is that the costs are obviously getting up. This is much more an oil and gas type of drilling operation to mid depths, to let's say 3,000 meters of depths. Yeah, and what you see then is, and this is in the lower right bottom graph, you see to the point where you have proven your resources, yeah, where you have your confirmation drilling done, already a couple of millions are spent. And this drilling of it is about half of these costs, yeah, that you have to spend. Yeah? So that's obviously where we can improve on. On the other hand, the good thing really for these mid-depths, and that's why we have so much focus on it, is that most of the wells, a lot of these wells, yeah, that are drilled in that region down to 3,000 meters, yeah, have sufficient yield. Yeah, so you have resources that you can efficiently produce, and technically we can drill there. So there's an example. The upper example here is from Munich, where 100% of the wells have been technically realizable. That goes down if you go to deeper resources, and that brings me to my next slide. Because these deep and ultra-deep resources, that's quite an interesting arena where there's a lot of focus on. On the one hand, technically drilling them becomes much more difficult. So the technical risks are really going up. The upfront costs are really going up. You need much more people. You need actually much more expertise to go there. But we are going into that arena of geothermal anywhere, that we're getting much more independent from our location where we are. And interestingly, you bring your levelized costs here for such a system, you effectively bring them down if you can effectively, technically drill to that depth. And I have there two nice examples from it, from two papers. And you see in the upper one is from advanced geothermal system, the lower one from enhanced geothermal systems, two studies. Yeah, and I start with the lower one, which is a recent study from US. Looking at that, and the first one here is 1 kilometer depth, and you see if you take $100 per megawatt hour as a threshold, there are only a couple of tens of sites where you could drill economically. Clearly, I mean this is 1 kilometer, but if you go to 4 kilometer or 8 kilometer, if you go deep, then you shift that much more economic solutions, and you go to 10,000 of potential sites where you could actually economically develop it. And that's the same for AGS. In principle, if you can construct that, if you can drill that technically, yeah, then we are bringing, you see that here in that curved blue arrow, yeah, then we are bringing the specific capital cost of this installation, we're bringing them down, and we're narrowing the spread. So really coming to solutions, yeah, that you can do in almost every site. Obviously, I mentioned already these costs are high. We're talking here about $100 of millions that you need to invest upfront. And there's a lot of optimization and innovation coming into that, yeah, really to help that, to bring costs down, to make it more efficient, these drilling. And let me talk about some really having these emerging technologies. Let me talk about this one here. And I start with shallow again, with the ultralight and light drilling rigs, yeah. Very interesting developments ongoing for the urban area. Yeah? And you see here on the left side, you see Hammerdrum. This comes from Switzerland, a small startup. We said we can do drilling much more like a mining process, yeah, at this point, or a tunneling machine process at this point, yeah, and bringing it to just a container. So you can place this one big container in your city and it drills your well bore almost automatically. And this functions with a system, yeah, with a hammer and reamer system that anchors itself into the well. It's operated on the wire line, yeah. then it fills up a container, pulls it out, empties the container with the debris, and goes into it. Yeah? So, and their concept is really this is slow, but it's cost efficient what we're doing here, and it's very compact for the urban area. Then in the middle you see the GeoMachine, GM2000, yeah, a very exciting project. They had a very compact rig that you see here. This is a pneumatic or an air-driven hammer that they're using, so really specialized for hard rock drilling at this point, but they could show with this very compact rig that they very, very cost efficiently drill even a 2-kilometer depth. Yeah? So this is for special cases where you at this moment do not need well control, yeah, if you look at that rig design. But yeah, this is very cost efficient, it's very compact, yeah, and it's fully automated. You operate that complete rig, that complete operations with 2 people, yeah, on a joystick, yeah, with a remote control. To the right, there's Hausmann. Hausmann, then we're going more to the design of a real oil and gas drilling unit type of, but everything compact on one trailer. So one big trailer, this is your rig, this is what you need for your drilling operation, complete with well control, with your platform on top of it. They can integrate even different drilling technologies with a specialized top drive that they have developed for this one. And this is really optimized for medium depths, yeah, in the city, so in urban areas, fully electrified system. Now let's move from the medium to really the deep. Hard rocks, yeah, the crystalline rocks. And there you have a whole world, let's say, of so-called novel hole-making technologies. A whole world of developments or projects that are upcoming with new systems, how you can remove your rock in front of the bit. And this is here percussion drilling. Percussion drilling is known, is very effective, let's say, for up to the mid-depths, yeah, with these air-driven hammers. There's a lot used as well, but the big challenge is always how do I bring that to depths? How do I work with drilling fluid? How do I work with mud? And I have here 2 projects I want to present. One is GeoDrill, one is Orchid. And GeoDrill really looked into remove all the valves that you need in such a hammer system, a mud-driven hammer system completely, with developing, with focusing on the so-called Geander effect. That's a fluid oscillator that producing these pulses that you need for your hammer downhole, yeah, without any valves in it. And they brought that really to the prototype level, tested that in shallow depths. Yeah. And then Orchid, another very interesting project where they combined 2 systems, and they actually combined a commercially available hammer with a high-pressure jetting. So it had a downhole intensifier to jet a groove around your hole bottom. With that, release the stresses of the hole bottom and make the hammer much more effective. Yeah? And again, they could really show that, bring these type of systems, they could bring that really to the prototype level. Both projects are recently stopped, but there might be coming more, yeah, with these interesting percussion drilling systems here. Another one, very exciting one, novel hole-making system is based on pulse plasma or electropulse drilling. And important is here the word pulse, because it's not a continuous plasma that is burning at your hole bottom. No, it's a pulses of plasma, like a flash, yeah, like that is happening. And these flashes actually happening in the rock. You see that in the small picture with the electrodes on top of the rock. And then this plasma discharge is produced within the rock and lifting of the cuttings. This is a very efficient process in terms of, let's say, rock removal on the one hand, very energy efficient. On the other hand, your wear on your electrodes is almost zero, it's minimal. Yeah? So you can drill quite long footage with such a system, which is one of the big advantages of pulse plasma. And, but the requirements for your pulse plasma generation downhole are quite high. So you need to switch fast below 500 nanoseconds, and you have these very high voltages of 500 kilovolts that you need for it. We are working together, we are working in a project that is called DeepLight. Yeah, and DeepLight is really looking into the full integration of this pulse plasma generation in your bottom hole assembly. So you have a turbine, you have a generator, you have a transformer and a pulse generator. You have that all in your bottom hole profile. So it's not a cable that you're running from surface. You have that downhole and take your energy from your fluid mud that you circulate. You see here 2 pictures. One is really a shallow test where the prototype was tested for drilling. The other one is our full-size rig that we have at TNO, and as part of the Deep Light project, we want to integrate that type of drilling system with our rig in a full drilling operation. Next one is novel hole from the novel hole making is steel shot drilling, a kind of abrasive jet drilling, you could say. And there are two exciting projects and that are really ongoing at the moment. And the steel shot drilling actually works that you have your nozzles, that you have in your bit, in your drilling bit, anyhow, and your accelerator, such a steel shot, high density, it hammers on your rock, it creates fractures there in the rock. Your high pressure fluid can enter that, propagate that fractures, and then the shear forces remove the cutting. So these kind of steel shots enhance or they modify actually your whole bottom. And both of the projects that you see here are combining, let's say, a PDC bit with the steel shot erosive action. So there's a hybrid systems where they combine the best of these both worlds. You will hear more about Deploy from Jan Jette, or from Deploy and from Canopus, from Jan Jette, in the next presentation. Because what Canopus did is even using that steel shots not only to make your drilling performance better, but to steer that system as well. So you have a novel directional control, you have higher ROP, you get enhanced bit life from this combination of these two drilling technologies. And with that, there's an effective way of producing multilaterals. With that, you can increase your productivity and produce much more resources than we can do nowadays. We tested that in our labs, for instance, in the cuttings flow loop. We see here in the pictures where we have circulated or shown what it means to transport these steel shots in your drilling fluid. And we tested it as well in our drilling simulator. The red one here, a big vessel, where you can drill into rocks under pressure. This brings me to an overview of these drilling technologies here, and you see now much more names than technologies I talked about effectively, obviously because there is more, and I needed to pick some where we're involved as well. And let me start here in that overview. Let me start here on the right side with the electromagnetic wave technologies. So you have QUASE and DeepU, two active projects going up on quite innovative. These projects really taking your energy from the surface. With QUASE, it's microwave. With DeepU, it's laser, taking it from the surface, bringing it to the downhole, and with that doing your drilling, actually a melting and spallation process that you do downhole there. They're both early in stage, and there are quite some challenges, obviously, to get your energy there, but very interesting to have very different concepts of hole making here. Then we have plasma pulse. I mentioned it. There are several projects going on to have these advantages of this system that you have this effective rock removal mechanism plus these bit life or these electrode life, to combine that really for drilling long well bores in hard rocks, in crystalline rocks. They're ongoing, and many of them they brought it to the prototype stage. Are working on that one. And GA Drilling, Liam will talk in a couple of minutes about their specific technology. They're working on plasma pulse as well, but they're doing even much more with a fully integrated system, for drilling for geothermal anywhere. And then hybrid in the center, a lot of technologies, obviously, because hybrid combining best of both worlds. You see here a lot of PDC, so existing PDC technology combined with a different drilling mechanism like steel shot. Jan Jette will talk more about it, but as well with jetting combined with laser, combined with percussion as well, which could be interesting in a way as well, to do that. And then the percussion world, I mentioned already, percussion is out there for very, very long and very effective for the air hammers, or pneumatic hammers, but then bringing percussion really to depths, you need to go for liquids, for drilling muds, and that's still ongoing, so there are various projects ongoing, and brought it to the prototype level. Let's see where this is going, really, because it is a challenge, but there are some new aspects like this Coanda effect, which works completely without valves, which would eliminate one of the big problems of having the percussion downhole at depths. And then, important to mention for me as well, rotary drilling, so the classical drilling with PDC bits here, that made quite some advantages as well. There's one is really guess you know the Utah Forge project, really driving forward, drilling hard granite rocks with PDC, very effective, high ROP, increase the footage to the bit life as well. And Fervo is doing that as well next to the Utah Forge site for their EGS project. So we see there's quite an optimization ongoing there as well. Yeah, but I say innovation is not only about efficiency, that's a big part of it, but is really, really about unlocking new frontiers, yeah, to see where can we be and how can we get there with our new technology, yeah, to open up these new frontiers. And believe it or not, 50 years ago, the PDC bit, they started as well, and they needed to develop that as well about 5 decades ago, and really started with single cutter testing to see if such a system can survive at these conditions here. And what you see here at this overview is really that coming from a work that we did for the IEA Geothermal, or together with the IEA Geothermal, they funded this type of work really to get an overview of emerging drilling technologies for geothermal energy provision. And yeah, there's an IEA report upcoming next year as well about that. With that, thank you for your attention, and back to Frank.
Yeah, thank you very much, Andreas, for a very interesting talk. We have some questions coming in, so I would like to invite the audience actually to put in more questions. First question on the list. If you would have to put your own money into one of these technologies, who's given this great overview, where would you put it, Andreas?
Yeah, thanks. Obviously a very good question. Yeah, and yeah, I would definitely focusing on a hybrid solution, because there's already, I mean, I mentioned that there's so many progress ongoing with the PDC bits, and this is such a developed system, and for two reasons. Yeah, on the one hand, you can make that much better with a different hole making technology, yeah, that you add to the already existing one, yeah, with getting more reach, to enhance your bit life, enhance your radon penetration on the one hand. On the other hand, you're not changing the complete world. You can hook up your system then really to existing drilling operations. Yeah? So that makes it so attractive to focus on a hybrid. And I mean with hybrid here, really combining it with PDC drilling technology and add there an additional mechanism to make it more effective. I would go for that.
Yeah, thank you very much. Another question, you mentioned medium depth. Can you define that? So, for example, you mentioned the Huisman rig. How deep could that go?
So the Huisman rig, I mean, what you saw here is the 100 and 150 tons hook load system. What they're working on at the moment is something like 2.5 kilometers, so what you could say. Yeah. So this is at range, but it's for me, medium depth is up to 2.5 kilometers, yeah, in that range, what we're talking about. So the resources that you usually, technically, you can drill them very effectively, and I mentioned that the yield is high enough as well. You can usually produce, your success rate is high in these operations. But I have to say, and there's interesting developments on that, even with much smaller rigs, with much smaller hook load, you reach to that medium depths. Yeah? So, and this is super interesting, in particular when you're thinking about that we have all these uptake of ball heat exchangers, so these closed loop systems, where actually your yield is well known, or what you get out of it is well known, yeah? That we bring that to larger depths, reduce spaces, so we need very compact drilling systems, yeah, and cost-effective drilling system to reach to that depths, yeah, to install that, yeah. So in terms of rig size, there's an overlap, but yeah, the depth is whatever the 2.5 kilometer range that we need to reach. Yeah?
And clearly there are lower temperatures, at least in the situation in the Netherlands, with a relatively mild geothermal gradient. How do you compensate for that? And are drilling technologies offering something for that?
To compensate for the lower temperatures. I mean, so what you need to, obviously, I mean, it's economics, right? In the end, what you need to do, if you need to compensate for the lower temperature or the lower yield, what you can get out of it, obviously you need to on the one hand, you need to get cheaper. Yeah, it's what it is. Yeah, in your drilling technology. What you can do as well, obviously, you can have lateral outreach. I mean, then then it's not depth, so it's the length of your well, and with that, let's say the length that you have available, yeah, for your, let's say, for your heat conduction, yeah, if we're talking about ball heat exchanger system, yeah. So
and diameter maybe.
Yes, but then we're talking open systems, yeah. And if it's about diameter, to say then usually, I mean, for the classical open hole systems, yeah, when we're talking about drilling to medium depths, then we need to have the larger rigs, yeah, because then we need to have sufficient capacity to have these big welds, yeah, to handle the casings, obviously, to install these systems, yeah, and we need to have the high flow rates. Then we compensate at that point, yeah, we compensate with high flow rates for lower temperatures that we get. But then we need to have the big enough rigs, yeah, to handle these operations as well.
Thanks. I have another question. This is more about the evaluation and the comparison between the different technologies. The question is, did you do some sort of multi-criteria analysis to compare them, or did you use another?
So what I did, I mean, that will come in the IEA report. I had a set of criteria, so that I put out, yeah. So, but this set of criteria is really what depth they can reach, yeah. So what kind of TRL levels they have, these technologies, yeah. And that's how I would not say ranked, yeah, because that's not what I'm doing. It was really about to understand what is out there. How much are they developed, these technologies, and let's say what is their way to market, so to see that, yeah, and that's what we use. So we have actually 9 criteria that we looked into it, yeah, and just they have a color coding as well in the end, yeah. So just to give you an expression where technology is, yeah, and for what it is. Is it depths? Is it hard rock? Yeah. What is the TRL level? Yeah. So what is the kind of application that you want to do with it? Yeah.
Well, thank you very much. There are a couple of more questions, but we'll save them to the end, because I would like to give the floor to Jan Jette to introduce actually the technology that you're working on.
Thank you very much, Frank. Great pleasure to be here as a founder of Canopus. We started about 5 years ago. 4 years ago, we started to work together with TNO. And I would like to start with an acknowledgement as well to the Cancer for West, who is funding the Delft pilot that we are going to conduct in January. But also TKI and the RVO, who is also supporting a great European project, Deploy the Heat, that Andreas mentioned as well. You can see here a great picture, I think, of the horizontal drilling pilots that we did in Switzerland with the directional steel shot drilling technology last year. It gives you an indication that we are working pretty far with integrating the system with actual hole-making equipment that is being used in the field. But I'll first go into an overview of what actually is DSSD, or directional steel shot drilling. Well, it is a drilling service. We don't bring the rig to the site, that's the rig contractor, but we can mount our system on any drilling rig that is active somewhere and specified according to the depth of the drilling operation. So we can apply this technology both in shallow, middle, deep, whatever the definition is. We can use it there. The components of the technology are steel shot, and we combine that with PDC drilling. In the first picture you can see the steel shot particles. They're pretty small, and we have selected them based on the hole cleaning capabilities of these particles. You have to add something to the mud, but you still have, of course, to circulate it and keep the well safe during the operation. Then you have to control the concentration pretty well as well. We keep it to 0.5 volume %, and we do that by a completely automated steel shot injection unit. And by keeping it at this low concentration, which is smaller than the usual cuttings concentration in the drilling mud, we minimize the burden. This is the only burden to the drilling system compared to conventional drilling systems. We can use any conventional mud with this. Then the particles travel through the drill string, reach the bottom hole assembly, which consists out of a steering sub and the Canopus drill bit. The steering sub is effectively, the whole system is a rotary steerable system, which has many advantages. By being able to rotate the string, you have better hole cleaning and a better reach of the system as well. But by the method, which I will describe in a minute, we can make this rotary steerable system, which is notoriously expensive, we can make it much more, much lower cost, so that we can apply it also in shallow drilling operations and any drilling operations for any depth. It's also an ROP booster. I will come back to that as well. Important to stress as well that the pressure bit drop is, in our case, around 50 to 250 bar. And there are other jetting systems that don't use particles. They go to very high pressures. We want to differentiate from these with the 50 to 250 bar pressure range over the bit. We don't have to modify the usual drilling systems that are being used on drilling platforms, which is a big advantage from operational efficiency point of view. The mud and steel shot circulation system is shown in the diagram on the left. It is important to keep the mud tank and the pump free of steel shot particles, and that's why we inject the steel shot particles after the pump when the mud is already pressurized, and we remove them from the drilling mud just before the mud reaches the mud tank. We remove them together with the rock cuttings and separate them from the rock cuttings by a magnetic drum separator. And then we re-inject them so the steel shot circulation system is closed, as well as the mud circulation system is closed as well. But the mud tanks and the pumps don't see the steel particles. We prefer the injection system to be automated because it is at enhanced pressure and you don't want an operator to be next to it. Apart from that, we also monitor the rig performance closely, and that is because we want to be able to balance the erosive action of the bit with the mechanical action of the bit. And the only way you can do that is by closely monitoring both the rig system and using that as an input for the steel shot injection. So this is kind of also a next level drilling automation system, which the oil and gas industry have been struggling to implement as well. That's another interesting story. But not for now. The drill bits. It was already mentioned, this is a hybrid technology mentioned by Andreas. The drill bits are polycrystalline diamond cutter bits. We have designed them together with Zerdelab and GPS drill bits. And we believe that we have used the latest on polycrystalline diamond compact cutter bits, and building on top of that with our steel shot erosion. We have done tests in limestone and concrete. Concrete is of course a bit simpler, but with limestone it's nice and hard, and you can do a reasonably better controlled ROP tests. On the top right hand side you can see the borehole drilled in Belgium limestone. You can see how smooth the borehole wall is, high quality. Also in the softer concrete, the borehole quality is great and you don't see any particles embedded in the wall or something like that. And what you can also see in both pictures is that the whole bottom is not the typical nice regular groove that you get with a PDC bit, but you can see here the impact of the jets that help out, making the whole bottom a bit more irregular, and it gives much better control grip of the PDC cutters on the whole bottom. You can also see in the long vertical picture in the middle that the jet configuration is asymmetric, and that's important for the next slide. No, that's important for the steering mechanism, which I will describe in the following slide. This slide it goes a little bit further on the bit-rock interaction, and that is extremely important for the relative penetration improvement that we think is especially important for hard rock drilling. This curve is horizontal axis is the weight on bit, the vertical axis is the rate of penetration. It's a very popular way to describe the bit efficiency for oil and gas wells. And what you can see is for rotary only that you have, say, an inactive area, then a steep incline of the performance, and at the end you reach the depth of cut, the DOC, where you have consumed all the length of your cutters and you cannot go faster. When you add steel shot to the system, then you remove rock because of the erosion itself. Of course, that increases the ROP on top of this ROP, but it also weakens the rock face as described by Andreas in his presentation. Like I mentioned, that increases the grip and that increases the ROP. If you go through to this graph, you can see that the curve for rotary and steel shield is moved to the left compared to the rotary only, and also that the founder point is increased as well. How far you can move to the left and up is not clear yet, but we have done a number of tests and we want to connect that to also a theoretical model by which we can explain that. But the lab test that we have conducted with the drill bit test facility of RCSG is that we have seen for the softer rock that we can go a factor 2 or 3 higher, and for the hard rock it was even above the factor 5 faster rate of penetration, depending of course on the settings of weight on bit, torque on bit and RPM, etc. It is definitely a big improvement on rate of penetration, but rate of penetration is not everything. Like Andreas again mentioned, bit life is extremely important as well. You don't want to drill for 10 minutes very fast, but you want to drill sufficiently long to be able to drill a complete whole section in one go. And we are working on that. It is a big improvement on ROP, and how much that will be, reported in publications next year on various conferences. Then the steering sub. Once again, it is a rotary steerable system, which means that the complete drill string is rotating, the bit as well. The bit has asymmetric nozzles, which means that if you have a device that changes the continuous supply of steel shield particles to the bit into a pulsed concentration, and you can correlate that to the rotation of the bit, then you can ensure that you erode more on one side of the hole bottom than on the other side of the hole bottom, and then you have a steering effect. It is as simple as that, and that is what we are building and testing at the moment, and which we have tested in Switzerland last year as well. We drilled a few bends in that Swiss mountain, and a confirmation that the system is working and that we can build the first field tools, and that's what we are doing right now. It is very energy efficient, this system, which is an indication that you need minimal amount of energy to steer, and that is an indication that you have much more reduced wear than when you try to steer with manipulating the torque on bit, the weight on bit, huge forces. Then you need very expensive systems that are hard to maintain on the rig side, etc. That's the reason why we think this is such an effective, simple, but very accurate steering system. Just a quick description of the type of drilling assembly that we have, especially for shallow drilling, that I will come to in a few slides. Up to 500 meters, then you can go from the drill pipe directly to the drilling assembly. The total length is about 10 meters for the drilling assembly. And the flexibility of that drilling assembly determines the build of the angle that we can drill. We can make it as flexible as we want, but for many of the applications, the 10 degrees per 30 meters bend is pretty effective and nice to have. So that's what we are focusing right now. The steering action is much faster, as you could see on the slide with the steering sub. You can go around the corner with the steering action 90 degrees within 3 meters, but of course then the assembly cannot follow. So this is a difference yet again from oil and gas field drilling, where the assembly stiffness is determining the flexibility of the curves and not the steering action. Directional module we integrated, so we have a complete drilling solution with the system and are independent of other vendors, interfaces, etc. Very quickly, 2 slides on where we think the impact of the technology is very clear. There was a study done by TNO and KB Energy on specifically the Slochteren formation. And on the top right-hand side, you can see the transmissivity map of that formation. You can see also that when geothermal becomes economic for the Slochteren formation, you need kind of a transmissivity that is yellow or turning further red. There is not that much yellow in the graph on the top right, and with our technology, by drilling multilaterals, and that has been proven already in the Paris Basin and in München, that is extremely effective on boosting the productivity. With the DSSD technology, we can drill multilaterals that conventional technology cannot drill, and then we can open up, move, say, the collar the economical map of the Netherlands for the Slochter Formation from yellow to blue, which opens up quite a lot of geothermal projects. Of course, when you have multilaterals, you also increase the chance of accessing good reservoirs, so also the risk of developments is reduced as well. For shallow, we will have a drill test, a pilot in Delft by the end of January. There we will drill through two borehole heat exchangers, a vertical one and a curved one. And what we want to demonstrate there is that the curved one is going to produce much more energy than the vertical one, and that we are able to drill such a curved borehole heat exchanger. It's a closed system. You can place one or two of these U-tubes on the inside, circulate only through that. It's not an open system, so you don't have any interference with the surroundings. Why are we thinking that this makes a big difference? If you look at what a group of curved borehole heat exchangers can deliver in terms of heating and cooling, then the length is longer because you can steer. You know that you're not going to collide with other wells. Even better, you can drill them away from each other, which is why you reduce the interference between the several borehole heat exchangers. You have additional length, and you have you drill deeper than the normally 150 meters that Frank mentioned as well. We go up to 400, 500 meters depth. That means that you have also a higher temperature that you can produce for the heating. If you add up all these factors, then that means that with only 5 or 10 of these type of borehole heat exchangers drilled from a smaller location, you can have as much energy produced as 50 vertical conventional borehole heat exchangers. A big impact, and that is what we want to demonstrate in Delft. And this is the last slide. Want to give a brief overview of where we are with the technology. Thanks to all the factory acceptance testing that we did at RCSG, we have de-risked the technology so that we can have the first, and the pilot in Delft, of course, that we have the first commercial shallow drilling operations. We expect to be able to do in up to 500 meters depth next year, and in 26. After a field pilot in Ede, which has been lined up as well as part of the pilot of the Deploy the Heat project, we expect to be commercial for 500 to 3 kilometers depth of drilling. And you can see the nice pictures of the RCSG facilities, the cuttings, flow loop, and the steel shot circulation tests were done there. The vessel with the drill bit testing, and the rig where we did the full assembly testing. Thank you.
Thank you. Thank you for also introducing the RCSG. And I think it's also, please reach out if you ever want to visit us and have a look at what we can offer. But it's an exciting development, I think. Given the time, I would like to switch actually to Houston, to Liam. I'm collecting the questions here, and we can take the questions for Jan Jette also after Liam's presentation. So Liam, go ahead.
Great. So thank you very much. So my name is Liam, Director of Engineering here at GA Drilling. At GA Drilling, our mission is to make geothermal anywhere a reality. It's in our DNA, it's in our name. That's what GA stands for. And we've got many different technologies under development to help us get there. One I'm going to focus on today is an innovative downhole anchoring and drive system for drilling hard rock faster, further, deeper, and most importantly, hotter. So as you've heard a little bit about some of the ongoing pilot projects, advanced geothermal systems like the ones from Ever, where you're drilling this network of well bores downhole, intersecting them to create that closed loop system. You've also got enhanced geothermal systems where you're drilling wells close proximity to one another and fracture in between them. What they have in common is they need long inclined or horizontal well bore sections to be drilled, a lot of them. And hard rock, funny enough, is hard to drill, and drilling can amount to upwards of 75% of the total geothermal well costs, and therefore a significant proportion of project development costs. The ability to drill longer lateral sections cost effectively is really key to project economics. So we've mentioned these great pilot projects. In the US, we've got Fervo drilling in Utah, indicated by the blue star on the heat map on the left. And then you've got Ever in southern Germany and Europe, drilling indicated by the red star towards the middle of the screen. What's important is that to scale these projects, you need to be able to drill deeper. So if you look at these heat maps, the upper ones are showing temperatures at about 15,000 feet, 5 kilometers deep. And you're looking at the orange areas. That's where the reservoirs are around 150, 175 degrees C. That's where people are typically targeting. You can see that areas are limited. And at those sort of depths, it's around about 10% of the Earth's surface. What we want to do, what we are doing, is making it possible to drill to 33 or 10 kilometer deep wells. And when you do that, you can see how the accessibility to those sort of reservoirs really takes off. And that's what we're enabling. That's geothermal anywhere. That's where 70% plus of the Earth's surface can get access to the types of reservoir heat that you need to make these projects economical. So geothermal wells occur in hard rock, ultra high strength hard rock, 30,000 to 50,000 pounds per square inch of compressive strength. That's around 200 to 350 megapascals, which is 2 to 3 times stronger than most hydrocarbon reservoirs. High strength rock, hard rock, is associated typically with high well costs. Why? Because it requires a lot of energy to drill. Energy, when it comes to drilling, scales with the strength of the formation. The typical drilling technologies can be limited in how much energy they can get down there at the rock face. That results in slow drilling. That results in more drilling days, and that ultimately results in more cost. Time is money. In addition to that, you have drilling dysfunctions, which will damage your downhole tools and wear out your drill bits, and also result in poor drilling efficiency. And then lastly, but not least, it's hot, right? That's why we're there, and that can have a big impact on tool life and reliability, but ultimately results in short run lengths, which means you have to trip in, trip out to replace damaged components or worn components, and that results in short run lengths of about 400 feet to about 3,000. You're seeing a lot of improvements now in convention technologies are getting those run lengths up, but as both Jan Jette and Andreas mentioned, the target here is to drill these sections, these long sections in one run. Okay. Now, if you look at the business end at the drill bits, and we talked a little bit about hybrid technology, it comes down to getting the energy, maximizing the energy at the drill bit to destroy that rock. And what it comes down to is torque and speed. So torque comes from the cutters, right? Those black things on the face of the drill bit. Nice image of a fixed cutter drill bit that's now pretty synonymous with hard rock drilling. It comes down to getting those cutters engaged with the rock. And you do that by applying a force. Now, when it comes down to soft rocks, like a soft sandstone, for instance, the rock doesn't push back as much, right? So to get that depth of penetration of the cutters into the rock requires less force than it requires to get that same depth of penetration into a hard rock like granite. And what that means is you need a lot of weight, a lot of force. In drilling terms, that's called weight on bit. And the ability to get the weight, to get the depth of cut, to get the cutters engaged, and then turn the bit is what dictates your rate of penetration, ROP, or how fast you drill. So to drill fast and also actually to maximize the life of the cutters, you need to have a high amount of weight on bit. Now, a really nice example from guys that are out there doing it today. This is from Fervo in Utah. It's published earlier on this year at the Stanford University Geothermal Conference. The quote, granite rock, renowned for both its rock hardness and its abrasion, poses a unique challenge where an extremely high levels of friction impede the ability to transfer weight to the drill bit. And simultaneously, you need more weight than typical oil and gas applications to drill those hard rocks effectively. So when you look at the section of a wellbore and the drilling process, your weight is coming from the vertical section, and you're putting compression into all of that drilling assembly or drill pipe beneath that point of weight to get the weight to the drill bit. So when you do that, you have compression, you have things like sinusoidal or helical buckling that can happen, and you have drag of the drilling assembly on the formation. Friction factors in granite are a lot higher than they are in conventional reservoirs. That robs the weight on bit. So you end up needing more, but you can get less in these applications. The solution brings us to our first technology is the downhole anchoring and drive system. So this system is placed just above the drilling BHA. It has elements in there which expand to grip the rock. and it uses hydraulic energy available down there to apply a weight via reacting into the rock to the drill bit. So this ability to create that weight on bit downhole directly above the drilling BHA helps eliminate that buckling, right? Because now you require less weight from the vertical section. You can also pull everything along using this system. It allows a lot more weight to reach the drill bit because you don't have that buckling anymore. It can apply more weight on bit. It also, a great benefit is allows extra control of the drilling process because you're right there at the drill bit within 100, 200 feet. You're able to sense what's going on and you're able to change the weight accordingly. A nice case study in a paper we published a couple of months ago at the Geothermal Rising Conference showed that by adding the downhole anchoring system into the bottom hole assembly in a well in Thailand, the longest granite well in Thailand that was drilled, this system could add an extra 70% of length into the lateral section just by the addition of that weight on bit downhole. That's massive for the ultimate economics of the geothermal prospects. This is the system. This is one unit of the system. The system comprises at least two. So it's powered by drilling fluid, keeping it nice and simple. It has an actuation system inside that diverts some of that fluid that's pumped through the system to actually do work. It has gripper elements you see in the middle of the screen, those rectangular elements there. They are energized by the mud and they expand to grip the wellbore. And then each of these units can apply about 30,000 pounds of thrust. So what's that? About 12 tons of thrust. And it can adjust that thrust up to 100 times a second to not only drill faster, but optimize the process and mitigate things like stick slip or other dysfunctions. It has smart controls inside there and feedback so it can monitor what's going on in the drilling process and then adapt what it does to improve and optimize. And then it can also communicate via CAN bus to other systems in the drilling assembly, your MWD tools, your LWD tools, your rotary steerable tools, to find out what's going on for them, send data to them, vice versa, and then optimize the process ultimately. And then it's modular, so you can put 2 of these in the drilling assembly. You can put 4 of them. It doesn't have to be an even number, but you need at least 2 to keep that continuous force and motion. And the key here with this system, it's like any other downhole tool. It's plug and play for the most part. So I can use any of the existing drilling technologies, a rotary steerable tool, a bent motor for directional work, and I can stick it in there and it's fairly agnostic and you just get all the benefits and no additional uplift in terms of complexity. Great. That in itself is super exciting, the plug and play nature, but what we see longer term is this is an enabler for a new way of drilling hard rock wells. So rather than having conventional drill pipe that's made above 30-foot sections that have to be screwed together, we actually replace that with coil tubing. So think of a steel hose pipe on a reel, for instance. Coil tubing is used today primarily for intervention, but there is some drilling work done with coil tubing. It can be tripped in and out of the hole 3 to 4 times faster than conventional drill pipe, requires less manual handling, so you don't have people having to make up connections on the rig floor. One of the great benefits for geothermal is you don't have to stop circulating fluids. So because you don't have to make connection, you can continuously circulate. And that's all important for keeping your downhole tools cool and within their operating window. You also have wireline communication. So now you get real-time data feedback from your drilling systems to optimize the drilling process and improve decision-making abilities. One of the limiters for coil tubing drilling, like I said, it's done today, but it's typically done on very small diameters. And you need bigger diameters for geothermal. It's that the coil itself, the coil tubing, has torque and weight limitations. But now because we have the anchoring system can pass most of those forces and loads into the rock rather than requiring to be transferred by the drill string, which is the key enabler to this technology. And just to give it some additional merit other than my good words about it, is that GE Drilling signed a multi-year development contract with Petrobras, Brazilian national oil company, to develop this technology for offshore deep water wells. Why? Because hard rock drilling technology is applicable in oil and gas as it is in geothermal, as it is in many other drilling applications. So where there's some great synergies there with, talk about transition and getting conventional oil and gas companies involved. There's some great synergies there between what they do day in, day out, overcome challenges, make it economical to drill, and what geothermal needs to really to scale. Okay, we've built the prototype of this tool. This is some pictures of it being tested in Slovakia, where our headquarters is. And then we've also taken that prototype to our Houston test facility, one of our investors' test facilities, actually, to be correct. And we tested it in a shallow well just to prove the gripping and anchoring concept, which we did. And then as a nice side effect, we also saw a significant reduction in vibration, just down to the action of those elements gripping the wellbore and helping to stabilize the drilling process. Okay, so in conclusion, to make geothermal anywhere the reality, we need to be able to drill cost effectively, deeper, further, faster. Hard rock is hard to drill, namely due to those high energy requirements. Getting more energy density into the drill bit or changing the rock itself through things like particle drilling or something exciting that we've got going on by using plasma to actually pre-fracture the rock and then drill it with a PDC. They're all very exciting mechanisms to get through this. Our anchoring system allows you to apply a lot more weight and therefore get a lot more bit engagement and a lot more energy that way into the drilling process. And that's what unlocks the geothermal resources. So increased drillable lateral footage. We show how the thrusting can help extend the lateral reach. Again, very key for the economics of geothermal projects. It can increase the rate of penetration through having higher weight on bits. And then it can increase that run length through prevention of damage to the drill bit and other downhole tools. We didn't talk much about the optimization that this tool can bring to the system, but these optimizations can significantly improve the life of the other drilling technologies in the drilling assembly. And then ultimately, longer term, 3 to 5 years out, this technology will be an enabler to coil tubing drilling for hard rock, which can really step change the cost of geothermal drilling. Thank you very much.
Thank you very much, Liam. We're running a little bit out of time, so if you have to leave, please, you would help us a lot if you can fill in the survey. We'll stay here for a couple of more minutes to answer some of the questions. So if you would like to stick with us, then you're more than welcome to. I would like to start with a question for you, Liam. For the GE Anchorbit system, what's the maximum anchoring diameter?
Yeah, great question. So very, very important that it can expand enough to grip the wellbore. So the prototype system we're working on today for our first pilot applications, it can expand those gripping elements to about 9.5-inch diameter in an 8.5-inch hole. My background is in development of downhole drilling technologies for rotary steerable tools. And that is better than most rotary steerable tools can accommodate in terms of a overgauge tolerance. In future versions, we'll have more. But, hard rock wells tend to stay fairly well engaged, because they're hard rock, don't have as many washouts. So we think 9.5 inches more than suitable.
Thank you very much. There was another question about hole size actually to you, Jan-Jette. So in the future, what kind of hole sizes can your system actually deliver?
Yeah, great. We focus now on the 6-inch hole size family, which means that we have bits and the system is lined up for 6-inch and 6 3/4-inch drilling for the shallow geothermal installation of borehole heat exchangers. We can also drill the 5, 7, 8-inch boreholes in the case of say boosting a reduced effective geothermal system. After that, we expect to be able to, or we will develop the 8.5-inch technology, building on the experience that we got with the 6-inch family.
Yeah, thank you very much. Andreas, did you take that into account in your overview to look at actually the sizes that can be delivered by the different technologies?
Not particular in the way that, whatever, in my criteria, the size that can be drilled is not a particular focus on. But what you see, I mean, in the way I've presented it as well, there are certain technologies that are clearly working much more for what you call the slim hole system, in particular if you want to have larger depth reach. And then again, for the larger hole, we talked about it already, the larger diameters, then you need to have usually more hook load to go to that depth. And there's a differentiator. If you look into your, let's say, drilling technology and rig types, there's a certain differentiator that some are really much more effective for the slim hole, and so others have the wider range really go then to the let's say larger holes, the 8.5 and bigger sizes.
Yeah, thanks. We also had a couple of questions to you, Jan-Jette, about basically the persistence of the system, and also what potential damage could the steel shot deliver to some of the tools? Did you look into that?
Yeah, no. So we have also during the test in Switzerland, we have circulated for a long while through the tubing. We tested the surface system, and no damage at all. You have to check for restrictions, obviously, up front as well, and for the connections and the drill string itself. We have not seen any damage to the components. So that's okay. Of course, very important was as well to check whether the steel particles that we circulate could have an impact on the directional sensors. We had directional sensors in the system and they were not disturbed by it. And there is good technical reasons for it, why not? But that was confirmed by the test.
Thank you. Andreas, you mentioned hybrid solutions. I have actually a question to Liam about it. The question is, would it make sense to add a pulsating force to the tool bit with a frequency that matches the material to drill, Liam?
Yeah, great question. I don't know if I've got a good answer, but I know the system can be capable of doing that. So, you know, the fact that we've got smarts inside our tool and sensor feedback and a very rapid actuation system mean that we can essentially play tunes through this thing for weight on bit. So if we find that there's a sweet spot where there is maybe this resonance that we can excite in the drill string. Resonances are usually synonymous with bad stuff when it comes to drilling because you get a lot of issues with vibration and shock. But there is mechanisms to be able to do things like that.
Thank you very much. Then, Jan-Jette, you talked about shallow drilling, probably in more unconsolidated formations. What about the hard crystalline rocks?
Yeah, no, we have done tests in granite, for instance, as well, and it was very similar performance as in the limestone. Actually, the limestone that we test in is a little bit harder than that, and the concrete with the hard grains also show that if you have inhomogeneities, then it's the same as with PDC drilling. You have to control it. Sometimes you produce a pebble more than you expect, but that's acceptable.
And in terms of the dogleg severity, do you expect differences between the different formations?
Yeah, so what we definitely have to do if you go through a soft formation, we always have to balance the PDC cutting action with the erosive action. So if you have a soft formation, then we go to much lower hydraulic parameters for the erosion, because you also have to go for much lower mechanical forces on the drill bit as well. And for a hard rock drilling, you have to increase both to keep the balance. For the directional control, we don't expect a change in performance. What we aim for now is the 10 degrees per 30 meters, because for a 6-inch borehole size, that is an acceptable bending radius for the drill pipe that we are going to use.
Would that change for 8.5?
For 8.5, you will have a bigger drill pipe that you will use, so it will be somewhat stiffer, but you can design for it as well. So if there is a need for, at least in the lateral section that you drill for an 8.5-inch section, that you have more flexibility, then you would have to select your drill pipe such a way that you have sufficient flexibility to follow a faster curve. In the end, like I mentioned in the presentation, the steering method can go around the corner very quickly. So if you have a flexible solution, more flexible solution than the drill pipe and for the drill collars that you use in the drilling, then you open up, say, the possibility to drill much shorter bends than was possible before. That's new compared to the old steering systems that always needed also the higher forces and the stiffness of the drilling assembly, otherwise you would destroy it.
Thank you very much. And Liam, there was some concern about the reservoir quality in Europe, but I think in other places as well. So when you really are able to drill deep, say beyond the 5 kilometers depth or so, what kind of technologies or what kind of opportunities do you see there?
Yeah, I mean, on the technology front, we've obviously heard some of the technologies from the guys at Canopus. You know, we're also building additional technologies that all complement one another. You know, the anchoring system is great for getting more weight on bit down there, and then we're going to have these hybrid technologies to help drill faster for a given weight on bit. You know, tripping time is a big problem. You have well control issues when you're tripping as well. So the things we talk about with the coil tubing drilling and speeding up the rate at which you trip, and also one of the nice benefits of coil is that you can continuously circulate while you're tripping, which improves well control as well.
Thanks. And then I got the final question before we close off to you, Andreas. A question from Belgium actually, and they're not blessed with that many aquifers, I think, in large parts of Belgium. So what would it take, and do you actually think there's potential beyond the aquifers, so beyond the open systems?
Oh, I think so, yes. To just, yeah, no, definitely. I mean, that's what we've seen right now, with all these technologies. I mean, on the one hand, they're the closed loop systems, yeah, and there's a drive to bring these closed loop systems even deeper and economically economically deep closed loop systems installed. I mean, Jan Jetter presented an approach, and he's going to try that soon, yeah, actually in January. On the one hand, you've seen the percussion drilling system. It's for hard rock, but this percussion drilling system from the GM2000, which is really can reach very economically, can drill to 2,000 meter depths. So with that, you get actually much more heat, much more yield. Yeah, so and then you can add a heat pump as well on top of this. Yeah, if you want to feed that into a district heating network, or if you want to use it as industrial heat or so. So I mean, there are opportunities. So that's the one. If you're really tight, I mean, if your reservoir quality is very low. If it's at the edge, you could still think of multilaterals, so obviously, yeah, so as one of the solutions. Or, yeah, I mean, you could even think of, this is a bit more far-fetched, but even going deeper, yeah, and engineer your reservoir. Huh? So we see a lot, but there's even, because these kind of the really novel hole-making technologies, some of them might even take longer still in the development. Yeah? But there are quite some emerging technologies where we can see there in the next years, there can be really an uptake, yeah, in the market, and they can really change things. Yeah.
So thank you very much. I think that's a nice message to end this webinar with. I think there's room for innovations also in a technology in a field that has been developing these technologies for decades. So again, thank you very much for your attention. Please fill in the survey. It also helps us to define whether this is useful to repeat or to have another webinar in the future. And with that, I would like to thank you very much for attending this webinar, and hope to see you soon somewhere. Thank you.